Hello, welcome back to Sri Sai Tech Edu YouTube channel. Read, Lead, Success. We have started with the first module. In that we have already done with the first chapter. Now we started with the second chapter. In second chapter, now we are going to study the second theorem, that is Thevenins theorem. We have already done with the superposition theorem. Now we will start with the Thevenins theorem. Thevenins theorem, what it states: in a two-terminal linear network containing energy sources and impedances can be replaced with an equivalent circuit consisting of voltage source with an impedance. Energy sources can be either voltage source or the current source. We replace all the voltage source and the impedances or the resistances into a single voltage source with an impedance. Okay, how we will do that we will see in the next point. The value of E dash is the open circuit voltage between the terminals of the network. E dash will be the open circuit voltage. Like if you open circuit this will be not there. If you open circuit, we measure across these terminals VOC, open circuit voltage or VTH, Thevenin's voltage, or E dash. E dash is the open circuit voltage between the terminals of the network. Then Z dash is the impedance measured between the terminals of the network with all energy sources eliminated. We remove all the energy sources like voltage source and current source, and we keep only these resistances in the network, and we find the resistance, that is RTH, or Z dash, that is Thevenin's impedance measured between the terminals of the network. Then but will not eliminate but not their impedances. We eliminate the energy sources but their impedance will be not eliminated. It will not be eliminated. So this is called the voltage source equivalent circuit. Now we will see the proof. Proof is important. See, if you think if this is a network, this network can consist of anything, like it can consist many resistors and a voltage source, current source. It can consist of anything in this network. This is the main one simple network with voltage source and the load ZR, and 1 dash is nothing but port, IR is the load current. This is the circuit. If you take example for this network, what it is, if you see this part, what it is there, no, this is a network. It is a network. Okay, this voltage source is E and ZR is ZR itself, load current and load impedance, and 1 and 1 dash is the port terminals. Okay, the network can be anything. Here 3 resistors are there. It can be with any other network also. Here just for example, network here is 3 resistors connected like this is shown. Now if you see from 9.8b, 9.8b is equivalent to 9.8a. 9.8b is equivalent to 9.8a. That is what I told. This network can be any network. Here they have took as 3 resistances. It can be any like in different form of resistance also it can be there. It is equivalent they are telling. Then if you write mesh currents, mesh equations for this and this. For this first equation, E is equals to I1 into Z1 plus Z3 minus IR into Z3 is the first equation. In the second equation, 0 is equals to minus I1 Z3 plus IR into Z2 plus Z3 plus ZR. Which I taught in the previous topics, KVL and KCL. Using KVL you can write these equations. Here they have took common. If you write in elaborate way, you will understand how these equations have come. If you don't know how to solve this KVL, that is mesh equations, you don't know how to write, please watch my video which is already uploaded in the YouTube, that is mesh analysis. If you see that, you will understand how these equations have come. Then from this you can take out the I1 value. I1 is equals to IR into Z2 plus Z3 plus ZR by Z3. From the 9.25 equation, from this equation we got this. We took the I1 value from that. By taking that I1 value, we substitute in 9.24. We substitute this I1 value here. If you substitute that, then what happens is You will get E is equals to IR into Z2 plus Z3 plus ZR by Z3 into Z1 plus Z3 minus IR Z3. E is equals to IR into Z2 plus Z3 plus ZR into Z1 plus Z3 by Z3 minus Z3. Why? Because we have took IR common. After taking IR common, you get, you do LCM, you will get Z3 square here. This equation you will get. After this, what we need to do is, this equation already we got in the previous slide, it is IR is equals to EZ3 by Z2 plus Z3 plus ZR into Z1 plus Z3 minus Z3 square. After this, what we need to do, we are simplifying this denominator, as it should not be hectic. So I separately did the denominator. Separately, simplified the denominator separately. What you will get? Z2 plus Z3 plus ZR, Z1 plus Z3 minus Z3 square. If you multiply these things, this into this and minus Z3 square, you get in this form. Then if you then you can cancel these two, then you will get this equation. So if you do the equations, or if you see these equations, you will understand. Substituting the denominator, we substitute this denominator again back to here in this equation. After substituting, what you will get is EZ3 by Z2, you take common here, you will get Z1 plus Z3, then Z1 Z3 plus again you take ZR common here, you will get Z1 plus Z3. Okay, after that what we will do, we divide numerator and denominator by Z1 plus Z3. If you divide numerator and denominator by Z1 plus Z3, if this is Z1 plus Z3, it is divided, this and this get cancelled, no. If we divide both numerator and denominator Z1 plus Z3, it is no problem. Anyway, it will be cancelled. So Z1 plus Z3, if you divide numerator and denominator, you get Z2 plus Z1 Z3 by Z1 plus Z3 plus ZR. As this Z1 plus Z3, this Z1 plus Z3 will be cancelled as we divide with Z1 plus Z3. From figure 9.8b, the open circuit voltage 1 and 1 dash terminals is the open circuit voltages at 1 and 1 dash. Actually, this at this point we calculate the E dash. Okay, for calculating E dash, how we calculate? At the open terminals of the, we remove this load current, we will not consider this load current, we calculate voltage across open terminals. So E dash will be what? E into the total voltage E. Voltage divider rule is applied here. What is voltage divider rule? E dash is equals to total voltage is E into the voltage is which resistance you want at Z3. Why? Because at this point open circuit means there will be no current passing through Z2. So there will be only one resistor, that is Z3 here. So if you consider Z3, Z into Z3 by Z1 plus Z3. Z1 plus Z3. This is the voltage divider rule. What we'll do, we'll take the whole voltage into the required voltage resistance, that Z3 by Z1 plus addition of Z1 plus Z3, the two resistances. And the impedance measured between 1 and 1, that is the ports 1 and 1 terminals with all energy sources eliminated, is we eliminate this by short circuiting it, and this anyway it is open circuited. This is anyway open circuited. We will take across this RTH or Z dash as this point. If you see here, Z1 and Z3 are in parallel. So Z1 Z3 by Z1 plus Z3. So this parallel is connected in series plus Z2. Okay, parallel you know how to find. If two resistances are there, Z1 Z3 by Z1 plus Z3 plus Z2, it is in series. You will get Z dash. Okay, Z dash. Then from figure 9.8, see load current, we remove this ZR, no, for calculating. After that, for the final circuit, we will add this ZR. Actually in the textbook they have not mentioned by removing the ZR, they directly took like this, but in exam you can remove this ZR or else you can keep like that, but in mentioning in the question you need to mention that open circuit voltage you are going to take. Open circuit voltage is nothing but there will be no current passing through this, will take across this points only voltage. So in the C network, if you see the ZR is main, we have take the ZR and Z dash and E dash we already got. We want load current across ZR, means what we need to do, I equals to V by R. V total voltage is E dash and resistance is Z dash plus ZR, as they both are in series, Z dash plus ZR, V by R. I hope you understood. We will solve problems so that it will be easy for you to understand, but proof is also very important. If you understand the problem, then you can easily understand the proof. I will start with the problem. This is one more circuit where it is given in the textbook. Draw the Thevenin equivalent circuit. They have not given any values for this. We will just see, like there is one E1, Z1, Z2, E2, Z4 and ZR. This is the circuit shown. They want Thevenin equivalent circuit. To get the Thevenin equivalent circuit and get the load current at the R, what we will do? What we will do is, we will consider first the Thevenin equivalent circuits at A and B. So this circuit will be eliminated. This circuit will be eliminated. This circuit will be eliminated means the circuit is not there. So we want terminals, this we consider as a load. So we will eliminate this. Then Thevenin equivalent circuit at AB is, you should find at A and B we need to find E dash. To get E dash, what is the voltage dividing rule? E dash is equals to total voltage is E1 into, we want voltage across which resistance? Z2. Multiply that with Z2 by the total resistance is Z1 plus Z2. Okay, Z1 plus Z2. Then after this you got the Thevenin's voltage across A and B. Now what we need to find? The Thevenin's impedance or the resistance. So Z dash. Z dash also you will open circuit this and you look into this AB terminals, you will find the Z dash. For Z dash, if you see Z1 and Z2 are in parallel, so Z1 Z2 by Z1 plus Z2 is the formula. Now you got E dash and Z dash. E dash and Z dash. Now what? You connect once again the whole circuit. What you will get? E dash is given. Now see, this circuit is totally replaced by E dash. Why? Because for this circuit at terminals A and B we already found the voltage and the impedance. So it is replaced by E dash resistance in series. This is what the Thevenin equivalent. No, all the voltage sources will be replaced by single voltage source and the resistance is a single resistance. Two resistances are there. We are replacing it by Z dash. Now what we need to do is, we need to find the equivalent circuit, finally equivalent circuit CD terminals. We need to find the Thevenin equivalent. So as there are two terminals, we are doing separately. If there is only one terminal, like in the proof only once you can do, but here there are two terminals AB and CD. So again we will find Thevenin equivalent at point C and D. How to find? What we will do now, we will eliminate this load. Thevenin equivalent we want at CD. Apart from that next network can be deleted or be removed. Then later on we can add it. Okay, for calculation easy, we are going to remove that. Then you will find the Thevenin equivalent voltage E double dash here. E double dash here. E double dash is equals to what? We want voltage across this. To get voltage across this, E2 plus and voltage across this resistance. To find voltage across this resistance, apply voltage dividing rule. By applying voltage dividing rule, we need whole voltage. What is the whole voltage? As you can see, it is connected in minus plus minus fashion. So E2 E dash minus E2 we need to do, or E2 minus E dash, based on which potential is more. If here 10 it is, if here is 5, then take 10 minus 5. If which is higher potential, you need to take first that. E dash minus E2 is the total voltage. Then we want resistance across which we want voltage across which resistance, Z4, multiply with Z4 by the total resistance what you have, Z dash plus Z3 plus Z4 divided. That's it. That is the voltage dividing rule. After doing that, what you will get is you will get as this equation. Then you need to find Thevenin resistance. As we know, we already removed this load current or a load resistance, and we look into this. So we'll get Z double dash. To get Z double dash, you look into these terminals and you short circuit the voltage sources. So how many resistance are there? 1, 2, 3 resistance are there. As you can see, Z1 plus Z3 is in series. So Z1 plus not Z1, Z dash plus Z3 is in series. Z dash plus Z3 is in series, and these two resistance combinedly is parallel with Z4. So Z1 Z dash Z dash plus Z3 into Z4 multiply by Z4 plus Z3 plus Z dash. Here Z dash plus Z3 is one resistance. That will be multiplied with Z4, and total resistance Z4 plus Z3 plus Z dash. This is what is the resistance we will find. After finding the resistance, we want load current across the ZR. Load current is nothing but end terminals, that is the load. We consider load every time in the right corner end, no? So we again remove these all. Why? Because these all have been brought into one single impedance, that is Z double dash, and this everything, this E2, E dash and E2 is combined to E double dash. So you got E double dash. So you remove other unnecessary things, and we will write again back this ZR. This ZR we will write. After writing ZR, we want now this IR. That means how much current is going through this load. If you want that, IR is equals to, anyway you got E double dash and Z double dash. So V by R. R is what? Z double dash is in series with ZR. So add Z double dash plus ZR. So V by R, you will get the current across the load current. Current across the load resistance. This is the how we will do the Thevenin equivalent circuit if there are two terminals, and we separately do first the initial terminal, we will find the Thevenin equivalent, then the second terminal. We'll see a sum based on this. It will be more clear for you. See, if you see here, it looks the same like a previous problem, previous examples. E and A, B and B are the two terminals. Okay. Now what we need to do? First, Thevenin equivalent at terminal A and A. What I did, you can do like this. It is easy way, so you will understand. I want terminal till A and A. We want Thevenin equivalent terminal A and A. So we can remove this circuit. So I didn't draw this circuit itself. Okay. You can remove that circuit and write. And 1 ohm, this other I have written in the same way. We want the voltage across the terminals, plus minus. It can be replaced by VOC or E dash or VOC, or V open circuit voltage only we want, no? So VOC also we can write, or E dash as a Thevenin equivalent at terminal A and A, E dash. So E dash or VOC is equals to, if you see, if you want voltage across this resistance, what we need to do, use voltage dividing rule. The total voltage is 10, multiply with the resistance where you want the voltage into 1 by how many resistances are there? 3 resistances. Add them all and put it in the denominator. 1 plus 1 plus 1, you will get 10 by 3. Now if you now we need to find the impedance, that is ZTH. For ZTH, what we will do, we will remove this voltage source and we will do like this. If you see, we will take the ZTH across these terminals. If you want ZTH across these terminals, this is 1 ohm, this is 1 ohm, and this is 1 ohm. As you can see, this and this are in series, you can add up. So 2 ohms is in parallel with 1 ohm. So 2 into 1 by 2 plus 1, you get 2 by 3 ohms. Okay, 2 by 3 ohms. Then Thevenin equivalent at the terminal B and B we are finding now. Now what we need to do, we already got E dash value, that is 10 by 3, so I have took that, and Z dash, it should be replaced by a series impedance, that is 2 by 3 ohms. 2 by 3 ohms, and the other circuit what is remaining, that I am writing it. And we want now the Thevenin equivalent at B and B. So B and B we need to be there, and the other part, that resistance can be removed. Just for the easy of doing, so I am removing 2 ohms, and later on we can add the 2 ohms for finding the load current. After doing this, VOC or the open circuit, at open circuit we find the voltage. E double dash is equals to this 5 plus voltage across resistance. We need to do voltage dividing rule. How we can do, as 5 voltage is higher than 10 by 3, we minus 5 minus 10 by 3 into the whole voltage is this, into multiplied by the voltage across which resistance you want, across 2. So multiply with 2 divided by how many resistance are there, add up, that is 2 by 3, 1 and 2, add up. So you will get E double dash. You will get E double dash as 65 by 11. E double dash as 65 by 11. Then Z double dash, how you will get? You need, if you see, these two are in series, 2 by 3 and 1. So I have added up. I am adding this. If you see, this whole circuit is in parallel with the 2 ohms. So 1 plus 2 by 3 you will add into 2 by 1 plus 2 by 3 is 1 resistance plus 2. Nothing but this is R1, this is R2, and this is R1, and this is, sorry, 1 second. Here 1 plus 2 by 3 is R1. Consider it as R1. Then 2 is R2. So R1 R2 by R3. R1 R2 by R1 plus R2. No. So R1 R2 by R1 plus R2. Understood? So that is series is in the two resistors are in series, and it is connected in parallel with the 2 ohms. So I've considered like this. We got 10 by 11 ohms. Then to find load current, what I did, you see, now I have to, now this whole this voltage source, this voltage source, this resistance, this resistance, this resistance, this resistance, this resistance. If you see, these 2 voltage sources are added up to into 1 voltage source, and all these resistance are combinedly, it has become as Z11. We have already found out that Thevenin equivalent is this only. We add up all the voltage or the current sources, not current sources, all the voltage source into 1 and all the impedances into 1, and add again the load current. We get 2 ohms we added to the circuit where it is. Then we want current in this 2 ohms. To find current in this 2 ohms, what it is? I is equals to V by R. The total voltage is E double dash by Z double dash is in series with 2 ohms. So Z double dash plus 2. Substitute the E double dash and Z double dash in the equation. So you will get 2.0312 amperes. One more thing I want to mention here is, this sum is there in textbook. The proof example which I have shown in the previous slide, that they have given correctly. But this sum, what is there? No, this sum in textbook, it is the textbook they have mentioned is Roy Chowdhury. So in that textbook, what they have done the calculation wrong. So please check it. Don't get confused by seeing the textbook. In textbook, the value something 1 point something it has come, and here also they have took it wrong. Here in the case of 65 by 11, they have took 10 by 11, and here the calculation also they have done wrong. Here 5 plus this voltage across this we should take, but they have took 5 minus, so they have done some mistakes in the textbook. So please follow this sum what I am doing in the video. This is correct answer. See, use Thevenin's theorem to determine Thevenin equivalent to that part of the circuit left of RL. They want Thevenin equal to the left of RL. So we can open circuit this. What I follow is better is where the Thevenin equivalent asked in the question. Till there you keep the circuit. The circuit which is not required you just remove, then later on lastly we can add. See, this resistor is not required initially. Lastly we can add. So what you will do is you draw in such a way that, see, 12 volts, 3 ohms, 7 ohms and 6 ohms, plus minus we want voltage across this open terminal, that is VOC. That is nothing but Thevenin's voltage. No, Thevenin's voltage. This is Thevenin's voltage. The circuit actually is RL is here. You can remove this RL. Why? Because we want Thevenin equivalent left of RL. So you can remove, and later on lastly while writing the whole circuit we can add that up. By using voltage dividing rule, VOC or the Thevenin equivalent voltage multiply 12 volts, that is total voltage, into the voltage across which resistor you want, 6 ohms, into 6 by total resistance is 6 plus 3, you will get 12, that is 12 into 6 by 9, that is 8 volts you will get. Then for Thevenin resistance or the impedance, what we will do? We will short circuit the voltage source. If current source is there, we will open circuit. As voltage source is there, short circuit. Then 3 is in parallel with 6 ohms, and then these two are in series with the 7 ohms. If you calculate this, you will get 9 ohms. After calculating this, we need to write the voltage source 8 volt source in series. This is what the Thevenin's equivalent, 9 ohms. Voltage source in series is nothing but the Thevenin's equivalent. This is what VOC or VTH, Thevenin's equivalent. This is RTH, Thevenin's resistance. Again connect the question. In question RL is there, no? They asked for the left of RL, find the Thevenin equivalent. The left of RL Thevenin equivalent is RTH is 9 ohms and VOC is 8 volts. Connected in series with the and then add up the load resistance RL back. This is the final circuit we need to draw. See, now the next question. Use Thevenin's theorem to find the current through 2 ohm resistor in the circuit. Here a little bit different they have asked. See, Thevenin's theorem need to be used to find the current through this 2 ohm resistor. We need to find. You will get confused how to find current through 2 ohm resistor. It is same. What they want, current through 2 ohm resistor is required. Then remove that 2 ohm resistor first. Then find the Thevenin's voltage and Thevenin's resistance at that point at 2 ohms. Then add the 2 ohms back and get the current in that 2 ohms resistor. Simple. We will see. Here. 9 volts connected to 4 ohms, 6 ohms, 4 ohms, 5 ohms. Everything is same. As I told, 2 ohms you remove. Why? Because we want current through the 2 ohm resistor. That is the load resistor. Remove that first. Then find open circuit. As we open circuit it, we find open circuit voltage across this. So you will get Thevenin's voltage. As you can see, 6 and 4 are in series. So add up. You will get 10 ohms. Then as there is no current passing through this, as it is open circuited, we can remove that 5 ohms resistor also. Then by applying voltage dividing rule, what you will get, V open circuit or the Thevenin's voltage is equals to total voltage is 9 volts into, we want voltage across which 4 ohms, so multiply with 4, and total resistance is 10 plus 4. You will get VOC or V open circuit or Thevenin's voltage is 2.571 volts. Now we want Thevenin's resistance. How to find Thevenin's resistance? You take the only resistances, keep only resistance in the network, remove the all other sources, that is voltage source you short circuit and current source you can open circuit. Here as it is voltage source you short circuit it. After short circuiting, there will be no voltage source. This 6 and 4 are anywhere in series, 10 ohms, and this 4 ohms and 5 ohms. As you can see, 10 and 4 are in parallel and in series with the 5. If you see, RTH is equals to 10 and 4 in parallel, no? So 10 into 4 by 10 plus 4 plus 5, you will get RTH as 7.857 ohms as the Thevenin's resistance. After finding Thevenin's voltage and Thevenin's resistance, what we need to write? Final circuit we need to draw. How we will draw? The voltage, Thevenin's voltage, that is 2.571 in series with the resistance, that is 7.857 ohms. This is the Thevenin's resistance and Thevenin's voltage, and connect back the 2 ohms which you have removed initially. 2 ohms. You want current through this 2 ohms. So to find current through this 2 ohms, you apply KVL. As it is only one mesh, it is very easy. 2.571 minus, plus minus if you consider, minus 7.857I minus plus minus 2I is equals to 0. Then I you will get it as 260.8 milliamperes. See how easy it is. First initially remove that resistance, then find the Thevenin's voltage and Thevenin's resistance, then put back the resistance which you have removed, then find the current through that resistance. That's it. Referring to figure, determine the Thevenin equivalent of the network connected to RL. Determine VL for RL equals to 1 ohm and 3.5 ohm. Here two questions they have done. What they have asked is Thevenin equivalent of a network connected to RL. So we want Thevenin equivalent of this circuit. Okay, of this circuit, and determine we want VL across RL when RL is given as first 1 ohms and 3.5 ohms. This is also easy. Initially, in before question we found the current through that. Here what they have done, we want voltage across this load resistance. By giving RL values, they have given two RL values, we will get different VL values there. We will see that how to do. Initially what we should do, we should remove the load resistance. After removing the load resistance, 9 volts, 2 ohms, 3 ohms, 1 ohm is same. You find voltage across the open circuit, that is the Thevenin's voltage. Then VOC is equals to VTH is equals to, applying voltage dividing rule, the total voltage is 9, multiply with the voltage across the 3 ohms we want. So with the 3 resistance, that is the 3 you need to multiply by 3 plus 2. So VTH you will get as 5.4 volts. Okay, now we should find Thevenin's resistance. How Thevenin's resistance will find? Remove all the energy sources, that is voltage source will become short circuited. You keep the only resistance in the circuit, look into the open terminals and find the RTH. If you see 2 and 3 are in parallel, plus addition in series with the 1. So 2 into 3 by 2 plus 3, you will get plus 1, you will get as 2.2 ohms. After getting RTH and VTH, what we need to do? We need to draw the circuit once again by adding the load current which you have removed. 5.4 volts and 2.2 is the Thevenin's resistance. You need to put back the load resistance. What they have given for 1 ohm and 33.5 ohm they asked. First initially you take RL equals to 1 ohm. So to find VL across this resistance, apply again voltage dividing rule. The total voltage is what? 5.4, and you want voltage across which resistance? 1 ohm. So multiply it into 1 by 1 plus the another resistance 2.2. You will get VL as 1.688 volts. Then for RL is equals to 3.5 ohms. How much you will get? Again apply voltage dividing rule. VL is equals to total voltage 5.4. You want voltage across which resistance? 3.5. So multiply with 3.5 by 3.5 plus the other resistance 2.2. So VL is equals to 3.316 volts. That's it. Next question. Employ Thevenin's theorem to obtain a simple two-component equivalent of the circuit shown in figure. And use your equivalent circuit to determine the power delivered to a 100 ohm resistor connected to the open terminals. Okay, first we need to find the, they've already given the open circuit. Here already they have given the open circuit. What they are asking is find the Thevenin's voltage and the Thevenin's resistance across this open circuit, open terminals, and connect a 100 ohm resistor across this open terminals. After finding Thevenin's equivalent of VTH and RTH, we need to connect a resistance across the terminals, that is 100 ohms. 100 ohms. After connecting 100 ohms across this open terminals, find the power through that 100 ohms. Here we need to find power. Okay, we will see that how to do. See, 45 ohms, 0.7 volts, then everything is same. And if you see here, what I've done is, here directly calculating voltage across the terminals is not possible. Why? Because there is a current source present to that terminals, so we can't directly find. So what you will do, first we will better short circuit the final terminals, then using mesh currents, that is I1, I2, I3, write the mesh equations, that is apply KVL to mesh 1, 0.7 minus plus minus 45 I1 minus 22 into I1 minus I2, as it is with respect to first mesh. Then if you calculate, you will get first equation. In the same way, apply KVL to mesh 2, you will get the second equation. I have told these procedures how to apply KVL for meshes in the previous videos. You can search it for the mesh analysis. You can easily find the mesh, apply KVL to meshes by seeing that method. Then here one more thing is that, here if you see, in the second mesh, apply KVL to mesh 2. When you are applying KVL to mesh 2, if you see, this current, there is only one current source, so this becomes a super mesh. So only I indicated with a dotted line, so you can remove that current source while doing it. By removing that current source, what we will do is that this currents will not remove, but you will take that currents in the equation. Like for example, see here, minus 122 I2 minus I1, it is same. Then minus 75 I2 minus this current source we are removing. As it is a super mesh, you can remove that. I indicated by dotted lines that it means that it is removed. If you remove, then you need to connect this third mesh current also, that is minus 220 I3 equals to 0. You should consider like this. If there is only one current source, single current source between two meshes, then the super mesh is added again. We will add this super mesh again. What we will do, by adding super mesh, the current across this super mesh 0.3 is equals to I3 minus I2. Okay, I3 minus I2. You will get the third equation. Why? Because I1 is, you don't know I1 component. There is no I1 component, so 0 I1. There is no I1 current in this. So minus I2 minus I3 is equals to 0.3 is the third equation. Okay. Across, I'll repeat this step once again. Across 0.3 is the current I3 minus I2. With respect to I3 mesh, first we should take I3 minus I2. So solving 1, 2, 3, we want the current across the end, short circuit, ISC. We want ISC. To get ISC, I3 is the ISC. The load current is nothing but I short circuit. Okay, ISC. SC is nothing but short circuit. You will get, by solving using calculation, you will get I3, that is equals to ISC is equals to 100.3 milliamperes. After finding that, what we will do, we will connect, we will write the resistors, only the resistors, and remove all other energy sources and find the RTH. So 45 ohms, 122 ohms, 75, 220, and this voltage source is short circuited, current source is open circuited. After doing that, what you will do, you will calculate that 45 and 122 is in parallel, and these two is in parallel, and these two parallel resistance is in series with 75 plus 220. If you calculate this, Finally, you will get 328 ohms. After finding this, what we need to do? We can find VTH. We can't here directly, we couldn't find the VTH. So only we find it out first I short circuit. This is another method to find VTH. As there are three meshes and there is a super mesh, that is a current source across the terminals. So we can't do directly VTH. So we applied KVL so that you will get the I short circuit, like the end current, the load current ISC. ISC and RTH. From that you can find the VTH. VTH is equals to what? V equals to IR according to Ohm's law. Here I short circuit into RTH, we will get VTH. So VTH will be 32.8 volts. We got VTH and RTH. We want those two terminals. That's why, because we need Thevenins equivalence. After getting it, what we will do? The procedure is same. Connect the Thevenins voltage in series with the Thevenins resistance. They asked power delivered across 100 ohm resistors connected to the open terminals. In the question they have told connect a 100 ohm resistor to this Thevenins equivalent and find the power delivered to that. Power delivered to 100 ohms, how we will find? P100 is equals to I square R is one formula you have. Applying KVL, you will get 32.8 minus 328I minus 100I is equals to 0. So I will be 0.0766 amperes. Then P100 ohms is equals to, you got I value, square it into 100, you will get the power across 100 ohms. Okay. So this is what the answer is. Next question. Obtain a value for Thevenin equivalent resistance seen looking into the open terminals of the circuit in figure by first finding VOC and IC. This is similar to the previous question. Here what they are asking, almost similar. There what we did, we found RTH and ISC and we found later VTH. But here they are asking first find VOC and then ISC, then find RTH. RTH, how we will find? RTH equals to VOC by ISC. We can do by using Ohm's law. We'll see how to do. Here there is no, one more thing. Here easily we can find VOC and VOC here. Why? Because there is no current source or something. There is only just resistance. You can easily find across this open terminals VOC. Okay. How we will see that now. First we will find ISC. Okay. How we will find ISC? First short circuit the end terminals. Why we want for ISC, it should be short circuited. ISC will be considered at the end of the third end load current. At load what you get, no, that is the short circuit current. So there ISC we need to find. Take clockwise mesh currents I1, I2, I3, apply KVL to mesh 1, you will get first equation as 2 is equals to minus 79 plus 7I2, and apply KVL to mesh 2, you will get 0 is equals to 7I1 minus 34I2 plus 7I3. After finding it, what you will get is that after that you will apply even KVL to the mesh 3. KVL to mesh 3, you will get 0 is equals to 0I1 plus 7I2 minus 37I3. Here this KVL, I have already made a video. As I have already made a video, I am not going in detail. Why? Because Thevenins theorem, this topic is Thevenins theorem. Applying KVL is very easy. If you have not know how to do KVL, please watch the mesh analysis video which I have already uploaded. Solving 1, 2, 3, you will get I3 is equals to ISC. Why? Because the mesh and the final mesh current is nothing but the short circuit current. So you will get ISC is equals to minus 5.2295 milliamperes. After finding ISC, we will find VOC now. VOC, they have given minus plus, then 10 ohms. 20 ohms and all, everything is same. As this is open terminals, will find the VOC, Thevenin's equivalent. So if this is VOC, the same voltage will be passing here also. So VOC, you take one node as VOC, another node as V1. Then apply nodal analysis. Nodal analysis also there is a video. If you don't know, please do watch. I'll explain here anyway once again. Apply KCL to node 1. Here if you see, there is no incoming current source anywhere, so 0 you will take equals to outgoing currents. Consider all other are the outgoing currents. If this is an outgoing current, this is also an outgoing current, this is also outgoing current from node. V1 minus of minus 2. Why? Because if it is plus minus, it is V1 minus 20. As it is V1, if it is minus 2 volts, as the sign is in minus and plus, so V1 minus of minus, that is V1 plus 2 by 10, then V1 by 7, then V1 by V1 minus V0 VOC by 20. We will get after rearranging the equations and calculating, you will get 41 V1 minus 7 VOC is equals to minus 28. Apply KCL to node OC, that is open circuit VOC. If you apply that, here also there is no incoming current source, so you take everything is going outside of the node. If you take in that way, VOC minus V1 by 20 with respect to VOC, then VOC plus VOC by 7. Then this will be not taken. Why? Because there is no current passing through it. It will be 0. This resistance will not consider. Okay. Then after doing that, you got two equations. From that you can easily find VOC, V open circuit, by using calci. VOC we will get as minus 185.3 millivolts. From VOC and ISC, by using Ohm's law, RTH is equals to VOC by ISC, V by I. If you substitute those values, you will get RTH value. After getting this RTH value, they asked Thevenin equivalent resistance by finding VOC and ISC. This is the method you will solve. I am doing different kinds of questions. Why? Because it will be easy for you also to understand. If this kind of question, you will know how to solve. So I am doing different kinds of questions. So please try to solve them. It will be easy for you. Determine the Thevenin equivalent of the circuit. Here dependent source is considered in the circuit. We will see how, if different source is given, how to solve. As dependent source is given, we will find first voltage across the terminals. That is V open circuit. That is, we will get the Thevenin equivalent by applying KVL to the mesh. As you can see, there is no current in this, 0 amperes going. So what happened? This resistance can be not considered. So if you apply KVL by removing this resistance, what you will get? 4 minus 2k into the current, what it is, minus 4. The current is moving in this way. Why? Because there is no current passing through that 3 ohm. The current is moving in this way. But the direction in the question, it is in opposite. So minus Vx by 4000. R into I minus the other voltage is minus Vx, that is equals to 0. By after doing this, you will get Vx, that is equals to V open circuit is equals to 8 volts. But to find, we can't directly here find by removing the voltage source and the dependent current source also, and you can't find the current resistance here. Why? Because you will get 5 kilo ohms. That is wrong. Why? Because the resistance across there will be some resistance across this current source also. We can't do that. But what we can do is, we can find current I short circuit, what we have done for the previous slides. No, same in that way. Current by short circuiting the open terminals and removing this dependent source, that is it is like a super mesh. By removing that current source, what we will do, we will find ISC. For finding ISC, we apply again KVL. By ISC is equals to 4 by either KVL or directly you can do, because anyway 2k and 3k is in series. So V by R, if you do, you will get ISC. 4 volts by 5 kilo ohm, we will get 0.8 milliamperes. So RTH we can now easily find. VOC by ISC value you will get as 10 kilo ohms. If you directly did, how much you would have got? 5 kilo ohms. That is wrong. Why? Because there is a dependent source across the voltage open terminals. You can't take like that. So if there is a dependent source in this way, then you need to find first I short circuit current, then from that RTH you can find by VOC and ISC values. Okay, this is one method. Next question. Find the Thevenin equivalent of the circuit shown in figure. Here also see dependent source is given. Which kind of dependent source is this? current dependent voltage source. Why? Because current, it is depending on the current dependent voltage source. We want the Thevenin equivalent of the circuit. How we can do, we will see. First 1.5 I 3 ohms. Then first what we need to do, there is a dependent source. What we will do, first we will short circuit, and here for this circuit we need to connect a 1 ampere at the terminals, so that it will be easy. If there is a sum like this, we need to connect a 1 ampere current for testing, for finding the Thevenin equivalent. After we need to apply KVL, that is taking this as a V. If this is V test across the current, this node will also be V test. So apply KVL to the V test node. Then V test minus 1.5 I by 3 ohms plus V test by 2 is the outgoing current. Incoming current, if you see here, current 1 ampere is incoming and other are outgoing. If you consider 1 ampere is equals to V test minus 1.5 I by 3 by V test plus V test by 2. You will get here I is equals to minus 1. Why? Because we are considering here I in the opposite way of what they have mentioned in the question. See, I here in the question it is given in this way, but we have to keep it as incoming. So I will be minus 1. Okay, I will be minus 1. If you substitute I as minus 1, what you will get, if you calculate, you will get V test value as 0.6 volts. 0.6 volts. That is what the Thevenin equivalent voltage, V test. RTH, how we can find across the terminals? RTH is equals to VTH by 1 ampere. V by R. RT is equal to 6 volt, 0.6 ohms. If something question like this is asked, why? Because it is depending on the dependent source. There is no independent source itself. If there is no independent source, it will be tough to find the VTH, RTH. So you need to, if you connect 1 ampere current also, there will be no difference. So 1 ampere circuit you connect across the terminals, and you can easily apply KVL. You will get V test value. RTH is nothing but V by I. I is nothing but 1 ampere we have considered here. Anyway, RTH will be 0.6 ohms. While doing with dependent source, be careful. Dependent source sums will be we need to find properly. If dependent source is there, or what are the methods also I am showing you. So only I'm doing different kinds of sums with dependent source also. So I've done different questions based on the Thevenins theorem, and even when dependent sources, what we need to do, and if there are different kinds, if there is a super mesh, how to find short circuit the load current, and then find the ISC in that way, so that you will get exposure to different kinds of sums, so that it will be easy for you if they asked those kind of sums in the question in the exam. These are the practice questions. These kind of questions I've already done in the previous slides. If you can compare with that and do, they are very easy. As you can see, this is try a 1 volt test source. 1 volt test source. There we have used 1 ampere as a test source. Here you take 1 volt test source as the, and they've given hint and answer also have given. Please try. If you have any doubt, you can put it in the comment box. I will see and I will solve and send. I'll try to solve and send. So that here I am stopping the video. We have completed superposition theorem, then Thevenin's theorem. We are left with 2 other theorems to complete the chapter 2 of module 1, and we also complete the module 1, whole module 1. Just 2 topics are left in this chapter, so that we can complete the module 1. In further videos, I will do the other topics, Norton's theorem and maximum power transfer theorem. For now, I am stopping the video. If you have any doubts, please do comment. Thank you. Shri Sai Tech Edu Read Lead Success YouTube channel. Keep reading.